This talk is going to be very high level because we're going to talk about multiple approaches to remove the GIL. But I will start with very quickly, telling you what CPython is, what the GIL is, and then we will talk about the various approaches, and finally we will talk about the latest one, nogil and PEP 703, and what we can expect. Python, CPython. Python is a high-level language. You can write in practically English. Computers can't run this. That's why you have the Python interpreter, which takes your program and converts it into bytecode that the machine can actually run. The standard reference implementation of this interpreter is the CPython. And CPython has this thing called the GIL. What is the GIL? It's the global interpreter lock. What it does is it says, let's say you're a thread, and you want to run some Python bytecode. Well, you need to have this lock, and as long as you possess this lock, you can run your bytecode. And then if you drop the lock for some reason, you stop needing to run Python bytecode, you have to reacquire it and wait to reacquire it before you can run any more Python bytecode. What this means for many programs is that even though you might have 100 threads, a maximum of one thread can run at one time. And when the GIL was made, this was not a problem, because at that time, most computers did have only one core. So you couldn't run multiple threads anyway. And so why not all languages have GIL? I think Python is one of the only major languages that has GIL. Why did we go with the GIL? I'm going to talk about one example, which is reference counting and garbage collection in Python. Garbage collection in Python, very simple concept. You have objects that a program uses. You stop needing those objects at some point during the program lifetime. You want to delete those objects so that your memory is safe. How Python does this is by using an approach called reference counting. So every object in Python, when you initialize it, has a reference count of 1. Let's say you say a equals 1. The object 1 has a reference count 1. And then let's say you say in the next line, for some reason, b equals 1. The object 1 now has a reference count of 2. And then let's say a and b get deleted for some reason in your program. 1 has no other object referring to it. Its reference counts drop to 0, and it can be deleted from memory. Now let's try doing this in the case that we have threads. And we're going to have only 2 threads, because that's all my brain can handle. And all these threads are going to do is they're going to refer to one object that already has a reference count of 1. So thread 1 reads the reference count into its own memory. It updates it, so it increments it by 1, and then it writes it down. Thread 2 does the same thing. The reference count is 3. Everybody is happy. But let's say the GIL didn't exist, and this update of the reference count, all of these 3 instructions need not always run together. GIL doesn't exist. These threads can do whatever they want. Then you have thread 1 reading the reference count, thread 2 also reading the reference count. Both of them update the reference count, and both of them write it. And we are 1 off. And the same thing can happen when you decrement the reference count. This was an increment example, so we are 1 less. And if you start deleting objects, you can end up in a situation where one thread expects an object to be there, and it's no longer there, which can lead to failure or bad memory. This is not good. And when it comes to decrement, you will be 1 up. And that means the object will no longer be deleted until program exit, which is not as bad as the increment case, in my opinion. So Python went with GIL. Why GIL? It was simple. It's very easy. You only have 1 lock, so there's no deadlock. There's no race condition. If you have this lock, you can do your job. If you don't have this lock, you got to wait. It's easy to implement, easy to get right. It also made C extensions in Python really easy to write. And this was very important for Python to grow as a language, because you have this really wonderful community of libraries. You can use anything. You have import anti-gravity. All of this happens because you could write these C extensions really easily. And the reason you could do this was you could depend on the GIL making sure that any shared object that you have is, you don't have to worry about blocks, you don't have to do anything, GIL takes care of it for you, you're very comfortable. And the GIL was a very good decision at that point in time because you anyway just had one core. The world has changed since then, and this is no longer true, and now we want true multiprocessing in Python. Now, there do exist versions of Python that don't use GIL. One very well-maintained example is IronPython and Jython. Both have no GIL. Their garbage collection does not use reference counting. There is also a version that I found, which is no longer maintained, and it was on top of PyPy, and it used software transactional memory, which is similar to how databases do it. And it was very complicated, but that one does use reference counting. And so now we get to the start of the history. Trying to remove the GIL is almost as old as GIL itself, and it starts with the free threading patch. What the free threading patch did was it said, hey, you have all of these global variables like reference count. We're going to keep all of them in one big C structure, and this C structure is going to be locked. And if you want to make any changes, you acquire this lock, do your changes, drop this lock. The problem is, in Python, everything is an object, and every time you refer an object, you're going to increment or decrement the reference count. And this meant there was too much contention around this one particular lock, and Python was 4 to 7 times slower, but the advantage was it worked. This version of Python worked. It was just very slow, and it had no API changes. This number, 4 to 7 times slower, is a number that I saw in many places, but there are also other ways of interpreting this number, which is going to be a common theme, especially when we get to further implementations. The point is, it was much slower and not acceptable. And so that particular attempt was dropped. And fast forward to 2007, I couldn't find any major attempts between 1999 and 2007, but there were a lot of requests, lots of open letters, lots of blog posts saying, hey, we have many cores now, and Python doesn't let me use these cores, and this is a problem for all sorts of computation. And this is a response from Guido, which gave us the first standard of what could be an acceptable thing to remove the GIL and why it's become so hard. CPython will not accept any attempts to remove the GIL that slow down single-threaded programs. This is the standard, and it's really hard to meet. Which brings us to the next attempt. This attempt is also no longer maintained. It was a little bit out there compared to the other attempts. And this, again, changed the garbage collection completely. So it went with the same garbage collection that IronPython and Jython use. The way it handled object ownership, so let's say you have a list or a dictionary, you want threads to change this. How do you allow them to change this? It did this by saying, unless you have ownership of a particular object, you're not going to be able to change this at all. And it did this using monitors in the same way concurrent Pascal uses it. In the end, it was about 30 to 35% slower, and this was dropped. This is no longer maintained either. Nothing happened, at least nothing that I could find happened for quite so many years. And then in 2015, we have Gilectomy, which is when I kind of found the whole attempts to remove the GIL. And that's why this talk is called the Gilectomy, because I am biased, and this is my talk. The Gilectomy lived for at least 3 years. And in those 3 years, its approach changed significantly. So towards the end, you had Larry Hastings, who is the one who led this project, talk about tracing GCs that we talked about before. We're not going to cover every single approach that he had considered. So I'm going to talk about the first approach that he had considered and why even that wasn't working out. So Gilectomy's main idea was you have all of these reference counts, and you need to update them when you have threads. And in 2015, the CPUs had become advanced enough that you had something called atomic increment and decrement, which is basically this concept where you tell the CPU, hey, I'm going to increment or decrement this integer, and I don't want any other threads that might ask for it to be able to touch it. So that operation becomes atomic, and no other thread can see that integer until that particular core is done with it. The problem is these are 30% slower compared to normal increments and decrements because of CPU architecture. The other thing that Larry Hastings did was he had locks on every single mutable object, like a dictionary or a tuple. Tuple is not mutable, like a dictionary or a list. This attempt also broke the C API badly because you have locks everywhere. You can no longer rely on Gil protecting any of your objects. So all of the C APIs would have had to be rewritten. In this attempt, it was also significantly slower for single-threaded programs. Directly from atomic increment and decrement, it was 30% slower. Locks introduced more overhead, so it was even slower. And even when you had multiple cores, the speed up that you got from the extra cores was not significant enough. Eventually, Larry Hastings, being very smart, actually got the program, this new version, the Gilectomy version of Python, to be comparable with the single-threaded version. But you needed to have 7 cores to be able to match the speed of a single core, which is not what we want. And eventually, it was just dropped. This approach never worked. Which brings us to the nogil project. It says 2022 because I got the number wrong. I am very sorry. So far, what we've seen is that there is a lock on mutable objects, and there is a way to handle reference counting. The nogil project is different because reference counting alone itself is broken down into a few different approaches, depending on the type of object you're doing reference counting for. So the first one is biased reference counting. So we know that from all of these approaches, if you try to make reference counting the update atomic, and you have multiple threads accessing it, it's going to be 30% slower. But nogil does use atomic reference counting. And it is not that much slower. How does this happen? What happens is, for every object, instead of having one field, which is the reference count, it's now split into 3. The first one is the ID of the thread that created this object. The second one is a reference count for the thread that created this object. And the third one is the shared reference count, which a thread that is not the creator can update. So the true reference count of a given object is going to be the sum of the local count and the shared count. Why did he do this? Well, it turns out in research, they found that an object is usually only used by a single thread. And if we allow this particular thread to have normal increments, it's going to be as fast as normal. And in the off case that a different thread wants to touch this object, we can do atomic increments, which is exactly what happens. Shared reference count is the only one that is touched by multiple threads, and it's the only count that needs to be protected. Local reference count is only ever touched by the ownership thread, the thread that owns this object. And what you're doing as extra work is you're checking if the thread that wants to do an update is the owner thread or not. So on average, this works out. It is going to be a little bit slower because we are doing an extra check, and if the check fails, we are doing atomic increment. But on average, it's not that bad. But then we come to objects like none, true, false, small numbers, empty tuples. These are going to be used across a lot of threads, and a lot of threads would increment and decrement a reference to them. So what do you do about these objects that are highly shared? You just make them immortal. They are not destroyed for the entire life of the program, and since the number of these objects is small, while memory use is a little bit higher, it is not so high that it overall slows down the program or makes it bloated, and you save on updating all of these reference counts. Now, we have other highly used objects, such as functions, and you can't not increment or decrement reference counts for functions because you need to destroy these functions at some point. So what do you do with functions? The solution was deferred reference counting. So what this is I'm going to talk a little bit about the interpretive stack. When something happens in Python, you have all these operations that the interpreter should run in a stack. And when you call a function, the function call is added to the stack. The operations that the function should do are added, and then the function is popped from the stack. When the function is added to the stack, you need to increment the reference to this function by 1, and when the function leaves the stack, you need to decrement the reference by 1. Now, instead of doing this update every time a function is added to the stack, you are going to say, I'm going to pause. I'm going to run the GC cycle occasionally, and whenever garbage collection runs, we're going to pause all of these threads and then go and check any functions that are still remaining in the stack, update their references, check if reference count of any function drops to 0. If it does, you toss the function out, you don't want it anymore, and if it does not, you leave the function be, and you restore the reference counts to what they were before the GC cycle. Now you might wonder, hey, you're doing these updates anyway, what are you saving on exactly? The idea is that some function calls between these GC cycles would have started and ended, and you don't have these extra counts. And this does increase the speed of this. And finally, these are all of the changes that have been done to reference counting in nogil. And what about mutable objects? What about lists? What about dictionaries? What about taking a dictionary and updating it to another dictionary? Well, you have locks. The locks used by nogil are faster locks, and they are apparently inspired from WebKit. These locks are extremely small. They're only the size of a pointer, and they are very good at giving uncontended access, which was very useful because we just saw in research that one object is mostly used by a single thread, and if no other thread is waiting for it, you really want the access to be yielded quite fast, and this does that. You also have the case when you have lots of locks, you have deadlocks, and it avoids it using 2 methods. The first one is really smart. Let's say you're waiting for 2 locks, and you get the first lock, and you're waiting for the second lock. You don't hold the first lock until you get the second lock too. This way, there is no single thread that has 5 locks, is waiting for 1, and another thread has that lock. They're all deadlocked. This doesn't happen because there is no holding of locks until you can actually access all of these locks. It also does another thing where it drops these locks implicitly. This seems to be not best practice, but we're apparently going with it because the GIL used to be dropped implicitly, and wherever these locks are dropped implicitly is also where the GIL was dropped implicitly. So we're going to keep it, apparently. That brings us to PEP 703. I've talked about a few of the changes that the nogil project has, and I haven't talked about the changes that nogil does to garbage collection. It does change it a little, but not too much. We still have reference counting. The reason why I'm not talking about this is While I was reading all of the discussions that PEP 703 had, I discovered that some people thought that the change to the GC is not required, so it may not make it to upstream CPython if PEP 703 is accepted. But whatever I've talked about will definitely go into upstream CPython if PEP 703 is accepted. So PEP 703, this is the first thing that you will see if you actually go to PEP 703. The steering council accepts it, but not very happily. It's very cautious, which makes us think maybe it actually won't go through. And the reasons that I could find were threefold, some of which were already touched upon in the first talk today morning. The first thing is that it breaks the extensions. This is what happened when we went from Python 2 to Python 3. It made adoption really slow. The break here is as significant. The upside of this is a few libraries were tested for compatibility with nogil, and they found that the changes required from the maintainers are small, but they are still extra changes. And there were a few packages tested. The downside is that there were a few packages tested, and we don't know if this idea that the changes are small is true for all packages, or if some major packages are going to require entire reworks. We don't know. And that is why there is this cautious optimism that so far it looks good, but maybe not. Sorry. The second thing is that there is, of course, a drop in single-threaded performance. Although nogil is extremely good at multi-threaded performance, like we saw earlier, you really gain when you have multiple cores from nogil. When you have a single-threaded program, you lose anywhere between 5 to 11%. Different benchmark in this course had different results, but the minimum was 5 and the maximum was 11. So there is a question of whether this is worth it for single-threaded programs, whether this is acceptable for everybody. We don't know. There still is a lot of discussion. And finally, most worryingly, a lot of work done by Guido in the faster CPython project may not be compatible with nogil. For example, specializing adaptive interpreter, which came with Python 3.11, a lot of the work is not compatible with nogil and needs significant rework if it is going to be compatible. This means that all of the work that already exists that makes single-threaded programs faster may not actually work, so the loss of speed might actually be higher than what we expect. What do? We don't know. We have to see how difficult this is to consolidate, and we have to wait. So what can we expect? This was already touched on earlier today. Nogil is going to be rolled out in 3 stages. Stage 1 is when it's distributed as an experimental build that people can try. This is already underway. There's 2 PRs that will probably be merged soon. This discussion is only 17 days old, so maybe give it a couple of months. But we can expect that this is going to be there really soon, maybe 3.14, maybe. But stage 2, it's the supported but not default phase, where nogil is a fully supported build. A lot of extensions are able to work with nogil, and more importantly, the API and ABI of nogil are stable from the experimental phase. And in this phase, the hope is that people start using nogil more often, maintainers start including it as a build that they support. But this stage, the estimates vary about how long it would take. The lowest that I saw and discussed was from Sam Gross himself, who wrote the nogil project, and he said, hey, we can do this in 3-4 years. There was less optimism from some other people who said, hey, this is going to take a minimum of 5 to 6 years. Please hold on. We don't want what happened with Python 2 and Python 3. Stage 3 seems to me, at least, as something very far in the future, where nogil becomes the default, and eventually the GIL itself is completely dropped. I don't know if that will ever happen, but maybe one day it will. And all of the effort of the last 20 years will come to some sort of conclusion. Which brings me to my own conclusion. I am very quietly optimistic about the GIL, so quietly that I decided to give a talk about it. I think it will actually happen. This effort has Meta behind it. Sam Gross works at Meta, and recently there was an announcement that Meta is going to put 3 whole people on this. So there's definitely going to be push, there's definitely going to be work, and maybe in 5 years we will actually have a very functional version of Python without the GIL. I should also note at this point that parallelism in Python there are other efforts to achieve this, which I have not talked about, because they don't touch the GIL, and I'm obsessed with the GIL. But if you're not obsessed with the GIL, you can look at subinterpreters, you can look at PyParallel. There are multiple approaches. This is not the only one, but this one is also coming. Thank you. If you want to talk to me, you can go there. If you want presentations or other talks that I've done, you can go there. I like talking about CPython. If you see talks that are not about CPython, maybe don't look at it because I wasn't that good, and those were my first talks. If you want to connect with me on LinkedIn, please do. Thanks.
Hi, great talk. You alluded to the idea that the GIL support, legacy support, might never be removed. Do you think it would be bad for the ecosystem or maintainers just to have both forever?
Both nogil and GIL?
Yep.
I'm not a maintainer, so I don't know. But the discussions are not conclusive. In the short term, if you have 2 versions of Python, you're going to have 2 versions of every single project on PyPy that you need to maintain. So that doubles the number of wheels. That seems to be the major concern over the next couple of years. And also the concern of if you have 2 modes where you can compile Python, you have 2 approaches of Python living together on the same repository. That adds extra complexity, which can lead to bugs and errors, and this is the second concern. Now, if these are sort of bars, I don't think so, because people do seem okay with it if it's short term. But if it's going to be like 5-6 years, I don't know.
Thanks, makes sense.
Would you have any concern about the speed of the implementation, like 5 years? Because it's a long time, with, especially in the world of LLMs and everything now. Like, could everything have just changed, I wonder, before they get around to this? Or do you think it just needs that amount of time and you can't rush it?
LLMs in specific are probably going to benefit from this because training them, maintaining them, running them can all be done in parallel. And nogil does have a lot of push from machine learning applications. So those in specific will probably benefit. Single-threaded programs, I don't know. If the fastest CPython work can be compatible or be made compatible with nogil, maybe this loss that we have temporarily can be alleviated, but as of now, I don't know, and there is no real consensus, words, difficult, consensus about this.
You mentioned that the C interface might be changing because of the nogil work. I know there's been a few other efforts to sort of rewrite the ABI a bit, like HPy and a few things like that. Do you know if they're working together, or are they sort of separate initiatives, or is that all to be decided?
I don't know if they're working together. I didn't see any references of any other change in any of the discussions that I read about this project, and I read quite a bit of discussions. If I seem sleepless, it's because of this. The ABI seems to break in exactly the same way it would break for sub-interpreters, and this is a question that I'm going to ask the steering committee member who's here. I don't know. As of now, there doesn't seem to be a lot of talk about working with other things. We have to keep in mind that Web 7.03, though, is very recently accepted, so there's probably going to be a lot more discussion around this.
Thanks. Any other questions? Anyone? No? Okay. Thank you so much, Sadhana.
Thank you.